Okay, let's take a look at problem number 34 from section 7.3. This is a complicated problem, and I've already made some modifications to the diagram here. To begin, we've got two circles, circle O, circle O prime, with centers O and O prime. There are two lines. The first, AB here, is tangent to both circles. The second, DC, is also tangent to both circles. These two lines, AB and DC, meet right here at point P. What we need to show is that O, O prime, and P all lie on the same line, this gray line that I've drawn in. We do not know that that is true. We have zero way of knowing that it's true. Any 2 points, you can draw a line through them, but not necessarily any 3 points. For example, I can't draw a line through these 3 points. Not one single line will cross all 3 points. I can draw a curve, but a curve's not a line. So this is quite the daunting task. All we're given is that we've got some tangent lines. So we're going to need to know a lot about tangency to show this. So now I have an idea as to how we're going to show that these 3 points all lie on the same line. We come up with some sort of special line between these circles, or this point here, come up with some special line like a bisector or something perpendicular. A perpendicular bisector would be good, or some sort of unique line. There's only one of those. And if we do that and we show that line OP is that special line and O prime P is that special unique line, then we've shown that that special unique line passes through points O, O prime, and P. Now, when I first started this problem, I wanted to do something with bisectors. I was looking and thinking, well, maybe if I draw a line AD and I show that OP is a perpendicular bisector, and I get that line OP, and I show that it's true. And then I take this other line here, O prime P, I extend it out, and then I show that it is also the perpendicular bisector. Then they'd be one and the same. But that didn't work out so well. And I saw that, I can draw some triangles here, so I started to look at the angles, and the angles down here at P are going to be what we're going to focus on. So before we get too far into this, let's draw some lines, and we'll keep using the hot pink. First line I'm going to draw OA. Let's draw some radii. We've got radius OA, we've got radius OD. These are going to be perpendicular here, and these guys are going to be congruent. We're going to draw a line OB, we're going to draw a line OC. These guys will also be perpendicular and congruent to each other. So let's start the proof. We've got OA is congruent to OD, AP. Now, I've got two tangent lines, and they meet at a common point. Theorem in the textbook, corollary 7.15, goes ahead and tells us that A to P and D to P are congruent. So we'll go ahead and we'll write that down. AP is congruent to DP, and that's corollary 7.15, and this was radii are congruent. Now, congruent angles. OAP is congruent to ODP since they're both right triangles, or right angles. OAP is congruent to ODP because they're right angles and they're congruent. That means that the triangles now, OAP is congruent to triangle ODP, and that's by the leg-leg congruency. We should have two legs, OA, AP, OD, DP, two legs congruent. The two triangles are congruent. That's good for us. What we're going to use it to show is that this angle is congruent to this angle. So with respect to the large angle ABP, or excuse me, APB, this line right here from O bisects the angle. So let's go ahead and let's write that down. This is angle APO, and that's congruent to angle DPO. By corresponding parts of congruent triangles are congruent. And that means that the line OP bisects angle P, or angle APD. And we'll write that out in full. APD. That's sloppy. Let's make that letter look nice. This is a proof. We want it to look pretty nice. APD. And this is, these two lines right here are what I marked in green above. That the angles are congruent, so this line from O to P bisects that angle. Next, we're going to shift our focus from this big circle O to the little circle O prime. We've got the same setup here. I've got these two sides congruent. I've got right triangles. I've got CP, BP, tangent lines. They meet at a common point. BP is congruent to CP. So we're going to repeat the same argument we just did with circle O, but instead of using these points on circle O, we're going to use these points on circle O prime. Likewise, O prime B is congruent to O prime C because all radii are congruent. Excuse me here. Line BP is congruent to line CP, and that's by the same corollary. That was 7.15. Then angle O prime BP is going to be congruent to angle O prime CP because they're both right angles and all right angles are congruent. And that's going to give us that triangle O prime BP is congruent to triangle O prime CP by the leg-leg congruence. And now let's take a look at what we've got. We'll go back to the diagram here. I've got two triangles, O, B, P, O, C, P. They're congruent, which means that this angle and this angle are congruent. And that means that with respect to this big angle, CBP, this line, O prime P, bisects BPC. Go ahead and we'll write that out. angle BPO prime is congruent to angle CPO prime by congruent parts of corresponding parts, which means that O prime P bisects angle BPC, but wait, angle BPC is the same angle as APD. Angle APD is congruent to angle BPC by the reflexive property. Fancy here, gives us a little bit more space. Those are congruent by reflexive. There's only one line that bisects an angle. OP must be the same line as O prime P. There exists a unique, that's the crux of this proof, unique angle bisector. And we're done. Because it's a unique angle bisector. There's not two of them. If I draw an angle, there's only one line that can pass through this angle such that it splits it into two congruent angles. Okay. That's it for today. Till next time, happy geometering.